In the previous lesson, we looked at the gradient of a scalar function. And essentially what this would tell us is, for example, how the temperature in a room will vary between 2 points. In this lesson, what we want to do is look at that operator, that vector operator that we use in a little bit more detail. And that operator is called del or nabla. And the operator is given by the partial derivative with respect to x hat, plus a partial derivative with respect to y hat, plus the partial derivative with respect to z hat. So these are all partial derivatives. Now, what is this operator by itself? Well, the operator is meaningless. It's an operator. It needs something to operate on. And that's what we're going to look at in this lesson. Previously, we looked at how ordinary vectors can multiply in 3 ways. We multiplied a vector by a scalar, we looked at the dot product, and we also looked at the cross product. In the previous lesson, we looked at the gradient of a scalar function. So in this lesson, we're going to look at the divergence of a vector function and also the curl of a vector function. So looking at the divergence, physically the divergence is how much something spreads out from some point. So here we see in this schematic that this particular vector has a large divergence. Here in the above equation is our operator, and here is our vector. Now whenever you take the divergence of a vector function, what you're left with is a scalar. Okay, so we take the partial derivative of our Vx component with respect to x, partial derivative of our Vy component with respect to y, and partial derivative of our Vz component with respect to z. So let's do this problem on the right hand side here. We have some vector which is given by this expression, and what we want to do is determine the divergence. So we have the divergence of the vector function VA is going to be equal to, now remember we take the derivative of our Vx component with respect to x, so we get 2x plus the derivative of our Vy component with respect to y, so we get 0, plus the derivative of our Vz component with respect to z, so we get minus 2x. And what we find is the divergence of our vector function VA is equal to 0. So that's the divergence of a vector function, and the divergence results in a scalar. We'll also consider the curl of a vector function, and the curl essentially is how much twist there is, or how much that vector will curl around some point. And here's quite a nice picture of a whirlpool. Now, the divergence of a vector function gave a scalar. The curl of a vector function gives a vector. So it has magnitude and direction. And what we're going to do is we're going to calculate the curl of the following vector function VA. Okay, so here we have our expression for the curl of the vector function, and we're going to use this in order to determine the curl of that vector function. So we have the curl of a vector function is going to be equal to, so we're going to do this one first of all. We take our Vz component and take the partial derivative with respect to y, and then we're going to work through this formula to determine what the curl is. So we have 0 minus the partial derivative of the Vy component with respect to z, so we have a 6xz x hat plus partial derivative of the Vx component respect to z, so 0 minus partial derivative of the z component with respect to x plus partial derivative of the y component with respect to x minus the partial derivative of the vx component with respect to y, 0, z hat. Okay, so our curl of VA is equal to minus 6x z x hat y hat plus 3z squared z hat. Okay, so this is our curl. Now while we've been looking at the first order partial derivatives, we also need to look at the second order. And I'm going to refer you to the Griffiths textbook to look at that in more detail. But the only one that I want to really cover here, and one that's going to come up time and time again, is the divergence of a gradient. And that gives us our Laplacian. So here we have the Laplacian of some scalar function t, and that results in the second order partial derivatives with respect to x, with respect to y, and with respect to z. Now let's suppose that the divergence, let's suppose that the Laplacian is equal to 0. So what does that mean? Okay, essentially, geometrically speaking, it gives us the curvature of a function. So if the Laplacian of t is equal to 0, it tells us that the temperature at one point is equal to the average of the point of the nearby points. So let's just calculate and finish up this lesson by calculating the Laplacian of the following function. So we have the Laplacian of t, a is going to be equal to, so we take the partial derivative with respect to x, we're going to get 2x, and then we take the partial derivative again with respect to x, and we're going to get 2, plus, take the partial derivative of this with respect to y, we're going to get 2x, and we take the partial derivative with respect to y again, and we're going to get 0, plus the partial derivative of 3z with respect to z, we get 3, and then we take the derivative again with respect to z, and we get 0. So the Laplacian of our function t is equal to 2. Now, as I said, there are a number of other second order partial derivatives, and I'm going to refer you to the Griffiths textbook to look at that in a little bit more detail. But this is the most important one which we will be coming across time and time again.